So, hi everyone, and this is session 2. So today we are going to do a bit more math. The idea is actually to review a little bit some of the tools that we are going to be using for the actual reverse derivation of the mean field limits. So it's still not going to be the full theorem today. We'll see the first ones tomorrow, but you should get a much better idea of what's going on and what kind of math we are going to be doing. So that's the plan. But before we go into all of this, right, there's a very important point that I want to discuss. So it's a sort of section 0 for today. And this is the initial conditions. Now, so again, let's say that we have a second order model, right? So I have something like this. We'll do it here. So I have something like this, right? And now I'm going to take the mean field scaling immediately. So we need initial condition if we are going to solve this, right? So we need the initial position and the initial velocity, right? For all I from 1 to n. And all right, if you're a little bit used to PD or any sort of or stochastic models, anything really with the time, right? Your reaction should be, well, I don't get to choose the initial condition, right? The initial data is given to me by the problem. Right, so that's a very natural reaction. And if that was the case, of course, I wouldn't need to do this section 0. The answer to that is a resounding no, right? This is not given by the problem. And there's a very, very simple reason for this, right? In the setting that we are studying, is that we simply have too many particles. And if I'm looking at plasmas, for example, right, which is sort of our simple physical setting, 10 to the 20 particles, right? how are you going to measure even remotely, right, the position and velocity of 10 to the 20 objects? And let alone the fact that measuring precisely the position of an ion is highly debatable, because we should really use quantum mechanics if we go to that level of description, and then you have Eisenberg principle, and you cannot measure accurately both position and velocity. But you know, let alone any of this, right? How on earth are you supposed to measure who's 10 to the 20? As a matter of fact, even if you could, right, there's no way you can. How are you even going to store the data for 10 to the 20 position, right? This is gigantic. I mean, 1 terabyte, right, is 10 to the 12 byte. Okay. So that would be, and measuring a position and a velocity, right, you need a 3-dimensional vector for each. So it's dimension 6, right? So it's probably something like 20, 30 bytes at least, right, for each particle, times 10 to the 20. Okay. So it's probably like 1 billion terabyte or something like that. So this is just not doable. And even for biological application, right, if you have only 10 to the 10 particles, it's still too many, right? I mean, biologists are very, very good at doing experiments, but they are not that good, right? There's just no way that if you have a population of bacteria, we can measure the position of all of them. So this is really not happening, right? So the best that you can hope for is to get some sort of statistical information on the distribution of position and velocity. All right. So the first big consequence of this, right, is, well, you can't just ignore the issue of the initial data, and you actually have to model the initial data. Again, this is very unlike, say, we were doing fluid mechanics, right? And then we could completely brush aside the question of modeling the initial data. Essentially, you know, that would be up to the experiment. Now, it doesn't mean that the initial data could be really very nice, right? There are plenty of ways to make experiments with fluids where the initial data itself is already singular from a mathematical point of view. But I wouldn't say we get to choose, right? And here we have to choose. So I'm going to review a little bit some of the classical assumptions and try to explain a bit why they are used and in which context they are used and all of this, right? And there's a first important case that is rather separate from the rest, and it's when you are using particles method. Right, such as peaks a particle in cell. Now, I'm not going to describe this method. Basically, this was a very popular, now a little bit less, but this was a very popular way of using many particle system to solve PDE or SDE, right? SPD. Right. And in that particular instance, you are not really interested in the particle system on itself, right? You're more interested in its mean field limit. So you don't really care that much about the initial distribution of particles as long as it approximates the right thing. And that will be clear in the rest of the morning how we would do something like that. And because you have a complete choice, it's not uncommon to simply pick them on a grid, for example. So you're going to have a certain grid, right? And then you're going to put a certain number of particles in each cell of the grid, so that this mimics the right the right statistical distribution. Right? So. And you will typically make sure that the particles are well spaced, right? You don't want them too close to each other. There wouldn't be any point in that. And we've seen that collisions create problems. So what you get is initially you have a deterministic, well-distributed cloud of particles. And this is a very, very special case. Again, because of how specific the application is. In essentially every other settings, the initial distribution of particle will be random to some point. Right, and so this is really the case that I'm going to focus here in those notes, right? This is random even if you have a deterministic system, right? So and so the randomness in the initial condition is really independent of the dynamics that you're going to consider, right? And it's just there because you think, well, I really don't know what is there, so I choose them randomly. Okay, so what kind of random distribution do we have? The simplest and most classical one is simply to take the initial positions and velocities independent and identically distributed, so IID. And this brings to the with itself the notion of chaos, which will be very, very important for us. All right, so we choose the xi0, the I0, right? IID. According to some given law, right? Okay, so this is obviously very simple. It's easy to do. Right. And nowadays, it's also very easy to parallelize if you're doing numerical simulation, which is, of course, a great point. And this corresponds to the assumption of molecular chaos that was introduced by Maxwell and then later used a lot by Boltzmann in the 19th century. Right, and so this is, I'm really not going to discuss much about Boltzmann's work or Maxwell's earlier insight into this sort of things. I just want to point out something highly remarkable there. So when Maxwell studies gas, right, and he puts this assumption of molecular chaos, which for us appears relatively natural because we have this idea that if you look at the molecules of a gas, they are very agitated. They go all over the place, right? But at the time, this is the 1850s, no one has ever seen any molecule, right? And physicists don't actually believe, most physicists don't actually believe they exist. Right. This is the very famous atomic controversy of the 19th century, which was actually only settled at the beginning of the 20th century. And chemists actually knew that there were molecules and there were atoms because they were seeing the effect of the fact that you have discrete molecules on the chemical reactions. But the mid-19th century for physicists, right, this is the time of Maxwell equations for electromagnetism, right? So for them, the world is a continuum, and you have waves and you have things like that. You don't have a discrete object, right? This is a crazy old theory from the antiquity was in large part discredited in many physicists' mind. Not all of them. And so it's, again, very remarkable that we get our first notion of gas in that context, and using this discrete version of the world that, of course, now we know is true. All right, so this makes a lot of sense, right? But is it true? Okay, and then physically speaking, right? If I take a plasma, is this true? Right. What that means is it says that there are no correlations between particles. And I'll give you a few examples later on where you'll see that at least at some scale, there must be some sort of correlations between particles. So the fact that there's absolutely zero is probably not true. So, of course, there's probably some level of correlation, right? Hopefully not much. How would we justify this mathematically? Right, on the initial data? Well, the idea, right, is if you start an experiment, the initial data doesn't come out of nowhere, right? Because, again, the plasma 10 to the 20 particles, you're not going to handpick them by hand and put them in a box where you want them to be. Right? So the initial data is really itself the result of long-time dynamics. Right? So typically, if you want to prepare an experiment, you're going to put the plasma there, you're going to wait, right, till you don't see anything moving, and you're going to say, okay, now we can start. Something like that, right? That's what I'm saying. Now, the dynamics is likely not the same one as the one you're going to use for the experiment, right? So there are plenty of things that you're going to do to prepare the plasma that then you stop doing when you start your experiment. Okay, so it's not the same system in general. And when you formulate the question like that, right, this notion of chaos is actually connected to very hard questions in ergodic theory in math. Right, and so ergodic theory is the type of mathematical theory and techniques that are trying to study the long-time behavior of dynamical systems, stochastic or deterministic. And so that's really one of the conjectures, that for many of those systems, right, the end result is ergodic in an appropriate sense, and that would imply some form of chaos. But for most practical systems that you can think of, this is only a conjecture. Okay. What about then, can we correct a little bit this chaos, right? So from pure chaos, let's go to something that would be chaotic. So almost chaos, right? And then why would I want to do something like that? Let me give you two examples, right? Let's say that our particles actually have a size. Okay, and let's do something super simple. Let's say they are spheres, okay? With some radius r, and of course r is super small, right? Well, there's a reason why you can take them purely independent, is that they cannot overlap. Right. So I need to have that xi0 minus xj0, right? I need to have that this is at least to r for all I different from j. And so what that means is, once I've selected some of them, right? Then the next one must be chosen outside of all those balls, right? So let's say we work on the whole space, it must be chosen in RD minus the union, right? From I equal 1 to k of whose balls centered at xi0 and of radius r. So there has to be correlations, some level of correlations. But this is small, provided that R is also very, very small. And now this is an interesting question, which is to ask, well, how small? What are we talking about here, right? So clearly, as R goes to 0, this will stop to matter, right? So the actual distribution is going to look more and more IID, but what are the critical scale? Well, there's a first one that is relatively obvious, okay? And that's, let's say that we end up putting them in a box, now a box of size 1, okay? Then you have a first critical scale, which is, well, the volume occupied by each one of them must not be too large, right? So if we're in dimension 3, right, that means that the volume of the sphere is essentially proportional to R to the 3, right? And you have n of them, right? So clearly, if the radius is that large, right, then you're in trouble. So cubic root, right, and this is 1 over n, 1 over d in dimension d, right? Then we cannot be close to an IID distribution. All right. So that is the first constraint, right, on the actual radius. Now, if you're much below that, then the distribution that you would get by making sure that they are away would still reasonably look IID, but maybe it will fail for a few pairs of particles. So you would still have some sort of vague correlation. So another way of formulating the question is to say, let me take an IID distribution, right? What's the typical minimal distance between two particles? right? So what do I mean by typical? I mean that there's at least a 50% chance that any two pair of particles is going to be above that distribution. Okay. So let's take our box example and let's say we pick them IID uniformly in the box, right? Right. So take n xi0, right? Uniformly, and of course IID, right? In a box of size 1, so in a box 0, 1 to the d, right? So we want to have a probability that you're never going to take two of them closer than R, right? So what is the probability that for all ij, right, xi0 minus xj0 is larger than R, right? Okay, so I pick the first one, right? Then I have to pick the second one in the remainder of the box, right? So the first one, I can pick it everywhere, right? So choice of x10. Now, the second one, I have to take it in a reduced volume, right? Which is 1 minus the size of the ball, right? So the size of the ball is going to be some omega d, depending on the dimension, right? The exact value will not matter much, times rd, right? This is the choice of x20. And well, the third one, now I have to exclude two balls, right? And you see where I'm going till, you know, the last one, I have to exclude n minus 1 balls, right? Right. And that is my probability. So that's the number I have to estimate. Now, you see that if this NRD, right, which was the scaling that I had here, right, if this NRD is close to 1, right, then this is a number that is going to be strictly less than 1, and I'm going to multiply a lot of them. So this probability is going to be exponentially small if okay, so that's why I said in that case, there's no way that this is happening, right? But now we have to calculate this product, and so let's assume that those numbers are actually small, right? Okay. So now I have a product of numbers, and all of them are close to 1, so it's a little bit more debatable, right? How big this is going to be. But I can still do some reasonably rough estimates, right? So as usual, when you have something like that, you can take a log, right? So log of p is going to be log of 1 is 0, right? So it's log of 1 minus omega d or d, etc., right, plus right. And so if all those numbers are small right now, I can do a Taylor expansion in the log, right? And so if I do a Taylor expansion in the log, what I get is minus omega d rd, right? Plus a big O of r d square, so r2d, right? And so on and so forth. Till the last term is omega d n minus 1 rd plus big O of this, right? So n square r2d. And so this now is something that can be easily calculated, right? And this is minus omega d n minus 102 times rd plus a big O of n cubed 2d. And so you see this other scale coming up, right? Which is such that this number, this n square rd now is of order 1, because that's the scale you want, right? So p is going to be, less than 1, right? So 1 minus p is going to be of order 1 if n square rd is of order 1. Right? And so that gives you, of course, that r is like 1 over n 2 to the d. Okay. Which is the square of this distance here. Okay. So that gives you a little bit of the range where things are going, right? So as long as the radius is less than this, you can actually use IID because they are never going to overlap, practically speaking, right? So with probability very close to 1, they don't overlap. Right? If you're in between, right? So you cannot use a strict IID because there would be an overlap, right? But for most particles, it's still going to be close to being IID. And if you're at n1 over d, then you cannot even be close to BIID for any of them. Right? So chaos is simply not possible. Now, of course, the rough analysis that I've done here, right, we should do it in a very serious manner and all of that, which I don't want to do, because I would spend one morning doing this, and then we have other stuff to discuss this morning, right? So this is just a very rough example of what's going on in a case like that. But you see that even though this notion of chaos, right, is very attractive, it has to be nuanced, right? In the sense that it really depends what you're going to do and what are the actual particles like and all of this. Now, a last reason why you may want to correct chaos is for energy, for example. Right. You might want to make sure that the energy is always bounded, right, with probability 1, not probability very, very close to 1, but with probability 1, right? And you end up having a very similar discussion as the one we've just done. It can be a little bit more complicated because the energy is a bit more painful, right? But so I'm not going to say more here. Again, that would carry us a little bit too far off tracks. Okay. So this is a little bit a rough idea of the initial data. As you can see, right, it's not as simple as the. Sorry, I missed a question. Well, 20 minutes ago. Sorry. Yeah, so m was the number of particles, and in that setting, it's a fixed number. But this is an actual very good question, which is why is it a fixed number? Because just as we cannot know the distribution of all particles, right? Well, for sure, we cannot know exactly how many there are, right? For exactly the same type of reasons, you're not going to count exactly the number of ions. Yeah, so this is actually a very good question, and we could take n random. I'm not going to do that here, but it could happen. I should say that there is one case. So I'm trying to stay away from the too much of the usual language of statistical physics. But you may have heard words such as microcanonical ensembles, canonical ensembles, grand canonical ensembles. And so in statistical physics, they refer to various type of settings, and in particular in the grand canonical, typically the number of particles is random itself, right? So also has some distribution, and this is important if you're moving away from classical mechanics, right? So if you're going into some settings in quantum mechanics, for example, the number of particles now may not be fixed along the dynamics, right? because you could have annihilations or creation of particles. And so then you could actually have a dynamics on n, right? Here, taking n random or not random will not going to change too much for us, because if it's a random number, it's independent of a rest and it's preserved. All right. So for the rest of this week, right, after this long discussion on initial data, what are we going to do? I'm going to take a chaotic initial data, right? And then one with actual chaos. Okay. According to some F0 of X. Now, a very important point on this, though, right, which will bring me to my next section. You see that we've reduced our initial data to actually one function, right, one law. And so, technically speaking, right, to find the law later on, we have to solve the whole system. But that is very, very inconvenient, right? Because if the only thing we know is one law, right, we would very much like to have a direct equation on the law. Right. And, you know, there are two issues here. Now and they are connected, of course. The first one, which will lead to the second, is we don't trust now the solution to the system for one particular initial data, right? Because it doesn't mean anything, right? We don't have information about one particular initial data. We have information about the distribution of initial data. And so this leads to the second issue, which is for this to make sense, right, in that context with the chaotic initial data, we need to solve the system for many initial data, many initial conditions, right? We need to pull out those random numbers, solve the system of ODE or SDEs, right? And then pull another set of random number for initial condition and solve again. And we need to do that many, many, many times. This is extremely costly numerically speaking. So that notion of initial data just made solving the system, right, a lot worse than it even was yesterday. And leads me to my first section. The first order of business is finally, we are going to do a formal derivation of the mean field limit so that we will have a mean field limit equation, and that will guide us when we discuss the tools that we are going to need to do a rigorous proof. Now, the formal derivation of the first mean field limit is actually super recent, okay, even at the formal level. The first example is actually due to Blastoff on plasmas in the 30s. In the 1930s, right? So this is much more recent than many other models from physics, right? I mean, fluids were well established by the 19th century, for example, right? And even actually collisional models were known before. So even though this is supposed to sort of be the simplest case, right? It's the one that was done last from the physical point of view. Now, you could argue, I mentioned Helmholtz's work on point vortices yesterday, and you could argue that inherent to that work is a derivation of the mean field limit. You know, that would be reasonably fair. But as such, and identified as such, it's really the papers by Blastoff that form the starting point. So what's the idea? Let me take now a sort of general example. So I'm going to write this down as a general stochastic system of first order, but with possible self-interaction. Right, so something like this. I am going to put the mean field scaling. And this is an exchangeable system, okay? And you can have a diffusion that scales with n if you want to. All right, so that's going to be our main equation for this morning, and I'm going to call that star, right? So this actually contains all the systems that I've written, because the second order model, you can always represent it as a first order by adding, defining the big vector of the two, right? So the capital Xi could be small xi, small di, for example. Okay, so what is the idea here? The basic idea is, what if all those xi, right, were almost independent, and since the system is exchangeable almost IID, right, then at time t. That's not a stupid question, right? Because we put them IID at time 0, so maybe we're still not so far from that at time t. Now, they cannot be strictly IID, right? Let's be clear about that from the start. They cannot be strictly IID because necessarily you have correlation between them from solving the system. Right. But what if we were not so far? I mean, we were doing something formal here, right? So we can hand wave at this point still. Then we would have a very simple reduction in that term, that sum. Because now I would have a sum of almost independent random variables, and I could apply a law of large number. Okay, so now let's define yj, right, for a fixed I. And then, of course, for j different from I, because yi is 0, right? So here I will load self-correlations, but the self-interaction, sorry, but right, with k of 0, so it's just a rescale. Okay, then the yj, right, they are essentially independent, right? At least if I know xi, right? Right. And hence the k of yj, right, are also almost IID. So we can apply a law of large number, right? And the sum of all those numbers should be equal to the sum of their expectation, or very close to the sum of their expectation. So I can remove I, right? Now I have to be careful. Right? For the yj to be IID, right, I need to know xi and I need to fix it. So when I take the expectation, it's not the expectation on everything, it's the expectation knowing xi. So it's actually the conditional expectation that I get here, right? And I'm going to stop for 10 seconds here to let that sink in, because that's very, very important. And it's a canonical mistake the first time that that people see this, that they fail to see the conditional expectation. And then you're writing nonsense, right? So is that all good for everyone? Let me check the chat. Right. Is that all clear for everyone why I have this conditional expectation in? Okay, seems to be all good. All right, so let me rewrite this not with the yj, so let me write the same equality, not with the yj, but with the xi, xj, right? What I wrote here is this. And this leads me to what is now known as a Makin-Blastoff equation, which is a first way to express the mean field limit. To Makin-Blastoff process, right? And I'm going to use bar because that's not our original process, right? That's something that we modified and we hope that they are close. Now I'm going to ignore the case j equal I in those sums, because anyway, that's a correction of order 1 over n, right? That's k0 divided by n, so I'm just going to throw it out. And that's our candidate for a mean field process. Now, at this point, you find this relatively horrifying, very likely, but it turns out that, right, because it actually looks worse than the beginning, than the one before, right? There are more terms in that expression. We kept the sum, and now instead of having a simple sum, I have a sum of conditional expectations, right? So initially, it might be hard to see why this is any better, but it is. So the first very important point to notice is that this one actually propagates IID. So if the xi bar 0 are IID, then the xi bar at time t are IID automatically. Right. All of them. Now, this is something we didn't have in the original system star. And this makes all the difference in the world, because now those complicated expressions, they become extremely simple. So let's give a name to the law, right? They all have the same one, so I just need one, right? This horrible conditional expectation, right? Now, just becomes a normal expectation according to the law. So this is just the integral of k xi minus y ft dy. Right? And so it's independent of j, at least as long as j is different from y, right? Hence, you have a very big simplification in this system, which is the following. Now, since I've normalized by 1 over n, I'm paying it here, right, with this n minus 1 divided by n, which I could take equal to 1. Again, this is a correction of order 1 over n. Right? And f is the law of xi. And you see here that, well, if I'm doing this, right, then I'm done, because now I don't even need the index I, they are all the same, right? So I just need to solve one. And now the n minus 1 over n, I'm going to replace it by 1, right? And I can drop the index y from the Brownian motion as well. And this is what I have. And this is my simplified Makin-Vlasov process. So that's the way to go, Makin-Vlasov process. Now I need to solve, well, something that looks like an SDE. It's not exactly an SDE, right? Because I need to know the law to solve the SDE. So it's an SDE that is coupled with itself, right? Thanks to this additional point. Right? But if you're more comfortable solving PDE, right? Out of that, I can get a PDE. Right? I can use Ito's formula. At least formally. To deduce a PDE. And then I get the corresponding forward Kolmogorov equation associated to VSD, right? Assuming F is known. So, but then this is all good. And then what do I have? I have this, right? Plus divergence of X of S, right? S of X. Plus this, and you see that this is what? This is the convolution of K with F. Convolution X, right? Times F. And this is sigma n square R2 Laplacian X of F. And if sigma n is a matrix, right, you should replace this by sigma n transpose times the second derivative. And this is our mean field limits. So in all of this analysis, right, what we've done is we've replaced this original complicated system by what turned out to be actually a much simpler system, right? This system 2 star, which looks very ugly, is actually super simple because there's no correlation at all anymore, and therefore all those terms are actually very straightforward algebraic expression, all the terms in the sum. And so if we can do all of this, then this very large system of SD or ODE can be replaced, your choice, right? Either one PDE or this Makin-Vlasov process, which is the coupling of an SDE with the law. All of this relies on a key assumption. If the xi is 0, right? So capital X here. IID, then the xi at time t are almost. IID. And this is called propagation of chaos. And that is the key thing that we have to prove if we are going to get the mean field limit. Now, I will note here that this is still quite fuzzy, right? Of course, it's a formal argument, but, you know, look at this almost, right? And you can ask in which sense. So we have to put measures, right? We have to quantify this, right? And there are several ways of quantifying this. And so you have actually several notions of propagation of chaos, right? Because if we quantify it in a different manner, then we could have propagation of chaos in one sense and not in the other. This is going to be our job the rest of the morning. Morning for me, sorry, it's afternoon on your side, to look at some of the ways that we can quantify this propagation of chaos, right? That we could quantify this propagation of chaos. And then the rest of the week, what we'll try to do is now use those quantified propagation of chaos in some cases to show results. Any questions at this point? What is the, sorry, there's a question in the chat that again I haven't seen, so 10 minutes ago. What is the physical meaning of this K in our equation? So K is the interaction kernel, right? So the K is the one that I discussed at length yesterday. So you had all those ways of doing interactions, right? So it could be Coulombian interaction with gravitational, so point masses or point charges. We saw the Biot-Savart law, right, for the point vortices. We saw again a Coulombian interaction, but then I mentioned two for the chemotaxis model. And then there was this very complicated with jumps, right, type of interaction for the neuroscience model. So is there any hope, another question, is there any hope to get the mean field limit, right, without the IID property? Yes, sometimes. But I'm not going to go there. This is a little bit tricky, and you need very specific examples. In general, you would not expect to have it unless you have propagation of chaos. But technically speaking, it could happen, right? Propagation of chaos, as we will see, essentially guarantees that the correlation in the one particle distribution are small, and that naturally leads to an equation on the one particle distribution. You could have a case where the correlations are not small, but you still have the equation, right? Some sort of miracle cancellation. Any other question? Okay, if not, I suggest that we take the break now for 15 minutes.
Pierre-Emmanuel?
Yes.
Yeah, I have a suggestion, which we usually do, is that during the pause, you can put in the share, I don't know, maybe significant equations or something that you would like to be seen carefully while we take coffee or any. Yeah,
And so you mean leave something on the screen, like leave the screen on that one, right?
Yeah, if you think this is the most to.
Yeah. This is really the one that we are going to discuss quite a bit. Maybe I'm going to leave the stochastic process first.
Okay.
That's our next step.
Okay. Thank you very much, Pierre-Emmanuel. We meet again in 15 minutes or in 20?
Yes.
Yeah, 15?
Yeah, 15, right? Not 50.
Okay.
So that would be what 3:45?
At 3:45. Perfect. Enjoy your coffee, Pierre-Emmanuel.
You as well. And I don't know if everyone is back. No, apparently not.
Yeah, I think yes. I think
You think yes? Okay.
we are more or less about 20. I think everybody's here.
All right.
You can proceed, Germany.
Okay. Thanks, Abdul.
Thank you.
And any before I continue, any questions that showed up during the break? No? All right. Then let us continue. So, how do we compare all of that, right? How do we do propagation of chaos? How do we formulate it, I should say, right? That's the question today. And so let's review a few very classical of those formulations. All right, and I'm going to start with what I'm going to call trajectorial approaches, and you'll see why. And the first way, which is going to go fast, but which should be stated and help explains also some of the distances that I will later use, in particular some of the Wasserstein distances. So the first way is simply to use the original system and the X bar. So this is the simplest, right? Because well, we have them, right? We have the xi and we have the x bar. So this is a very straightforward ID. So you have your system. I'm going to write things down. Right. Versus our limit, right, which is the x bar is equal to s of x bar t plus this thing, right? Okay. So this is the original system star, right? This was the Makin-Blastoff process. Okay, so to compare them, we can do exactly the reverse of the argument that I showed you before the break, right? So I can create several copies of the X bar, right? Just, just enough copies so that I have one for each of the xi. Right, so I have x1, x bar n, right? And then recall that in that case, right, this object, this integral, was actually equal to my sum, right? Of the conditional expectation. Plus, again, this correction of order 1 over n. Okay. And now I can compare, right? So I have to be a little bit careful, right? So when I take those copies, right, now I want to have this x bar I, right, plus the interaction term that I'm not going to rewrite. Plus sigma n dwi, right? Now, let's be very, very careful. It is essential so when I take a copy of the Brownian motion as well, right? I need to make sure that it is the same Brownian motion, right? The same Wi that we are using because if you change the Brownian, of course, the trajectory are not going to be the same, right? So this is absolutely essential. And similarly, right, when taking copies, I want to copy exactly the initial condition. At least almost surely. Because again, if you mess up the initial condition, right, then you're going to fail the comparison. All right. In one sense, sorry. In one sense, the PD is understood. I'm not going to discuss that right now today. Okay. We'll discuss this a little bit tomorrow and a little bit Thursday, but I don't want to talk too much about in which way the PDE is understood or even the SD. I'll mention a little bit of it later on, right, when we deal with the PD, but for the moment, I'm just pretending, right? because we are building the formalism, so I don't want to go into the technical details of, you know, you need the solution to be in LP, you need the solution to be sub F, and so on. Try to keep the chat open and visible so that I don't miss other questions. All right. So is this point about taking copy clear for everyone, right? Because again, otherwise there is zero hope that it's going to be working, right? I can very easily take the wrong copies of X bar and they won't fit with the Xi, and then they won't fit, right? And that's the thing that if you have a random variable, right, the law does not determine the random variable. Okay, you can have several random variables with the same law. So again, when taking copies, you need to be careful, right? And you need to make sure that the randomness is the right randomness for the system that you want to compare them to. Don't see any question. Okay. And then we can simply compare Xi and Xi bar. And for example, we can look at the following object, right? Right, so I can take various LP, discrete LP norms of everything, and then take the full expectation. Okay. And if you take P to infinity, so you can take a 1 over P inside, you can take a 1 over P outside, right? So you could also have something like this, right? The soup over I of xit minus xi bar t. Right. Okay. So this is a relatively simple idea, and this is the first method that we'll try to implement tomorrow. Now let's go to something a little bit more complicated. So we would like to compare sometimes directly, right? The stochastic system with the limiting PD. So that's a little bit trickier because now how do we compare a discrete system with a continuous limit? Not as easy. And there's this very, very useful notion here, which is called the empirical measure. I'm going to call it mu n. And you get it simply by putting Dirac masses, right? At the position where the particles are. Right? And so this is the empirical measure. Yeah, it has a very natural interpretation, right? Which is mu n of t and of a set O, right, is simply the proportion of particle, right, the ratio of particle that belongs to the set. So very, very simple. Now, mu n is a measure, right? It's a radon measure. On RD or whichever space the xi belong to, right? And it's actually even a probability measure. As you see that it's positive, total mass is 1. But it is random. Okay. And this is independent of whether you have Brownian motion in your system or not, right? Because the randomness of mu n, it just comes at the minimum from the randomness of the initial data. Right, so this is true even if you have no diffusion, right? So if the system is actually deterministic, because the xi0 are random, right? We took them IID. So they remain random, and therefore, if I take any expression out of them, and that includes mu n, right, it's random. So still, mu n is a random object in a fixed functional space. For instance, probability measure and RD. The limit, right, is also a probability distribution. So now we can try to compare them, just as we would compare two probability distributions. All right. So how do we compare two probability distribution? Well, there's a very bad idea, right, which is the total variation. So let's get this out of the way. Let me explain why it's a bad idea. So the total variation would consist, right, in taking the norm of this, right? So this is really like taking the mass of the difference as a measure, right? So something that I can write like this. But since F is likely to be a density, right? So it's likely to be absolutely continuous with respect to the Lebesgue measure. The total variation with respect to a sum of Dirac mass is at least is the sum of the mass, right? So this is actually 2 automatically. If S is absolutely continuous. With respect to Lebesgue. All right, so yeah, this is a really, really bad idea because, well, you know, 2 is not going to converge to 0, right? So this is not going to give us any sort of useful quantitative version of propagation of chaos or anything that we can use, right? So we need to use some sort of weak distance on the space of measure. Okay. So what are examples of weak distance? Let me show you some of the more common ones. I can take the W minus 1 norm, right? In general, I could take other negative sub-F norm, but W minus 1 is very simple, right? And by the way, if I want to compare them, remember that mu n is random, right? So down the line, I probably want to take some expectation at some point, unless I'm very, very, very good, and I think I can actually control everything point-wise, which. So this is just the soup of all test functions, right, that are in W1 infinity and that are bounded in W1 infinity. So you want that phi in L infinity is less than 1, for example, and gradient phi in L infinity is less than 1, and then this is the integral of phi x mu n t dx minus ft dx. And because this has a relatively simple expression, right, it has been a popular distance for mean field limits. There's a variant of that which consists in using Wasserstein distances. And now, Wasserstein distances are in general a more complicated type of object, right? And if I take two measures, right, mu and nu on RD, the WP Wasserstein distance to the power P is the result of a complex minimization process. So I need to look at all transference plane. So transference plane are object that depends on two variables, x and y, right? And they are probability distribution, so on R2D. And then I need to integrate something like this. Tx, ty. And I want the transference plane to have the right marginal. So I want that if I integrate pi with respect to y, right, then I have mu of x. And if I integrate it with respect to x, no, I have mu of y, right? Now, this is a bit of an abuse of notation when I'm writing here, but I hope it's clear enough what this is. And now, finding an exact expression to a Wasserstein distance is not super easy, except if p equal 1. And if p equal 1, this is sometimes called the Rubinstein distance. And it's actually very, very close to the W minus 1, 1, because W1 of mu and nu, right? If I take two variables now as the soup. And remember that for the W minus 1, 1, I was taking the soup over all functions that are bounded in W1 infinity. And here it's almost the same, but the function itself doesn't need to be bounded. I only need to bound the gradient. So a very similar expression. And there's a reason why Wasserstein distances are extremely popular. And that's because they are a very good fit with our previous type of distances. And this is something that we can make very precise. So let's say that mu is a sum of Dirac masses, right? And let's say that mu is also a sum of Dirac masses with the same number, right? It's the same n, and that's very important. If you want the expression below to be correct. Then in that case, actually, we can calculate relatively easily the Wasserstein distance. Well, relatively easily. We can write an expression. Calculating it would be another matter numerically. That's because it is actually the LP norm. between the discrete LP norm between the xi and the yi. Up to relabeling, right? Because here the xi and the yi, I can put them in any which order and I get the same measure. So when I'm going to calculate the distance between mu and mu, right, I have to have an expression that does not depend in the order in which I took the xi or the yi. So I need to make sure that I allow a permutation of one of them. And then this is the infimum over all sigma, all permutation of Sn. Right. So you see that this Wasserstein distance, right, the WP of mu n, the empirical measure, and F, this is a natural extension of our discrete LP norms. On xi minus xi bar. All right. Any questions here, guys? Nope. Okay. Then let's go to our last section, which is quantifying chaos. Statistical approaches. So up to here, right, we were still working at a somewhat discrete level because we were still working with random objects. And another point of view is to say, well, we're only interested in the statistical distribution at the limit, right? Because we are trying to calculate this law. The law does not in itself contain the randomness. So couldn't we immediately go to a statistical distribution of the system? Okay. Well, there's a first naive approach to that, which is to say, well, yeah, you know, I have a system of coupled SD, or a question from Abdu. Why should the Wasserstein distance be well defined? Yeah, not a hope that I can answer that this morning. So this is obviously a good question, right? If you look at the expression I've written here, it's not even clear why this is a distance, right? So why would it satisfy the triangle inequality, for example? Okay. So there's quite a bit of work to do for that, and it has been done, right? This fits within the general umbrella of what we call optimal transportation, and people have worked quite a lot on that since the earlier formulation due to Monge and then the improvement by Kantorovich. Yeah, even why it's bounded is not clear, right? Because you need assumptions on mu and nu, for example, right? And what are the minimal assumptions for on mu and nu for this subject to be bounded? This is not very clear. What people generally assume is that you have moments, so that the integral of x p d mu is bounded and the integral of y p d mu is bounded, and then the resulting distance is bounded. Right? If we're going to use this kind of distance, right, we'll need stuff like that. And well, we'll have to discuss all of this again. This is for tomorrow, right, mostly. Okay, yeah, so back to the full joint law, right? I have n particles. Well, let's look at the law. So let's define Fn of T, x1, xn, which is the law of x1, xn at time t. Right. Now, let's make something clear here, right? This is an object that does not contain trajectories anymore, right? And that's because if you really wanted the full law of a system, you should take the joint law of the trajectories and not the joint law of the positions, right? But again, that's what we want. We want a statistical distribution. This contains the full statistical distribution of the system. And formally, it solves a linear RPD. All right, so if you have an ODE, right, the law of the ODE solves what is called the Liouville equation. And if you have an SDE, this is usually called the forward Kolmogorov. I might end up calling it the Liouville equation, and in both cases, most of the time, just out of habit, but okay. And here it's an equation in dimension n, right? Which reads like that. Now, in spite of the name Liouville, it's interesting that this equation was actually first derived by Gibbs, as it is, in the 19th century. And in many respects, Gibbs played a super critical role. I don't want to go into the a historical description of statistical physics, because first of all, I'm not super competent, and second, that would take too much time. But when people think of mean-field limits, continuum equations, and things like that, right? Again, the names that come back, the main names of the 19th century is Maxwell, Boltzmann, right, for the first kinetic equation, the Boltzmann equation. But Gibbs is really the first one to have introduced a rigorous framework for many particle system to derive an equation like that, and to understand what is the entropy of such a system as well, which I'm going to briefly talk about this morning. So really very important contributions. Now, this is all good and well, right? But this is a very crazy equation. We should say that immediately. Because what we've done, right, is we replaced a system of ODE or SDE with many 10 to the 20 of them by a PDE in dimension 10 to the 20. So to say that there is no hope of solving this equation, right, is understating everything, okay? There is even no hope of actually storing a function in dimension 10 to the 20 on even the most sophisticated computer. Okay, and then imagine if you were only to discretize with 1,000 points in every direction, right? 10 to the 23 numbers you need to store. This is out of reach, completely out of reach. Right? Maybe if we have quantum computer one day, right? But even then, very unlikely. So this is a crazy equation in that sense. So what do we do with this, right? Good question. Well, of course, if the xi were IID, right? We would have a simple expression. Because now we would know that Fn, right, is tensorized. That's how independence is translated on the law, right? If you have independent processes, their law is the product of all the laws. Right? Now, because of our assumptions, this is true at the initial time. So at least the initial data is a relatively nice object. right? And this I will denote it in the following manner, right, to save a bit of space. Okay, so you know, fair enough. So a basic idea is compare Fn and tensorize the limits, right? Using some norm, some distance. The problem is there are major difficulties in doing this in large dimension, right? Because the dimension now is not fixed, it's moving. Now, for example, those are probability distribution, right? And now they are smooth probability distribution. So they are absolutely continuous with respect to the Bbjky measure. So what about going back to that a very basic idea and say, let's use L1 norms, right? And that works well in principle because this equation, it preserves the L1 norm. So, you know, of course, I'm saying this so you know that it has to be bad, right? So, right, it seems like we are cursed with this L1 or total variation norm. Whenever we are trying to use it, it is bad. The reason it's bad is relatively obvious. Let's say that Fn is indeed tensorized, but I just made a tiny mistake, right? So I don't have the right function. So let's say that I have a G, right, instead of F. Now that can easily happen, right? There's no reason why if it's tensorized, it's exactly the right law. They should be close, but exactly the right law? No, probably not. Well, the problem when you're comparing two tensorized functions like that, it's a very simple calculation to do. This behaves like n times the L1 norm on F and G, right? So we could have that F minus G is very small, but Gn minus Fn is of order 1. So this is very, very unfortunate. But this is the curse of dimensionality, right? If n was of order 1, this would not happen. We would be fine. But because n is very, very large, we are facing things like that. And again, if n is 10 to the 20, right, the factor n that you have here, it's not something that you can wave away. It's there. So there are very few quantities that one may use. Okay. And I'll leave it as is for today. We'll go back to this on Thursday. And I'll show you how to use the Gibbs entropy to do an effective comparison. Any questions on this joint law? Nope. Everyone is okay. Is that the almost IID? Yeah. So right. That's something we would like to exactly right. That's something we would like to make into a notion of propagation of chaos, right? But you see that here I'm a little bit stuck. We're trying to give a proper definition of what it would mean almost IID, right? I would like to say that we almost IID is if f index n minus f tensorized n times, right, in L1 is small. But that doesn't work. That doesn't work because I could actually be IID, right? But with a slight mistake, a slight error on the law, right? So I'm IID, so I have G tensorized n instead of F tensorized n, right? And F is very close to G, but they are not identical. And so I could be IID again with a slight error on the law, and I would not be able to see that if I'm using this L1 norm, right? So here I'm really missing, when I'm trying to look at this joint law, I am really missing what should be the right quantity, what should be the right comparison between Fn and F index n and F tensorized n times. Right. But again, we'll come back to this. Right? You have to wait till Thursday morning, but we'll talk about that. Any other questions? Nope. Okay. All right. So the joint law is painful, right? And it is painful because it lives in a very large dimension. Okay. Can we use another law? So there's this notion of observables or marginal, right? That are also promising. So what is the observable of a system? The thing you can see. So an example of something that you can actually measure if you have an experiment is the one particle distribution. I'm going to call that Fn1, which now depends only on one variable, and which is the one particle distribution. Right? So it's the probability of finding any one particle, right, at some point of a domain. Now, since the system is exchangeable, right, Fn1 is actually equal to the law of x1, and it's equal to the law of xi for any I. Okay. The system is exchangeable, it's symmetric, right? I choose the same law for every one of them initially, so they keep having the same law, right? They're not necessarily independent, but they have the same law. That's given. Right? That's the one thing that is propagated. Right. Again, be careful. I'm not saying they are independent. I'm just saying they have the same law. So the law of xi is I'm ignoring all other particles, right? I'm just following xi. And that's the same as following x1, as following x2, as following any one of them in law. Right. So then I have I can take more than one, right? I can take 2, 3, any number, right? So let's define f and k, right? Which is a function of k variable, and which is the law of x1t and xk of t, right? Again, pick any k of m, it's the same. So this is an object, right? And this is an elementary statistical distribution, right? So fn2 is actually measures the correlation. Right? In the system. Measures the correlation because it's the law of x1, x2. So you'll get some measure of how much x1 is correlated with x2. Right? Makes sense. And those objects are, we can connect them with the 2 objects that we have already defined. So obviously, if I take all of them, right, so f and n, well, this is just fn, and this is just the joint law, right, that I had introduced before. And generally speaking, you see that f and k, right, can be obtained from f and k plus 1. Just by integrating in the extra variable, right? And so if I want, I can do that recursively till I hit the joint law of everything, so fn, right? So this is the integral of fn. Right, integrated with respect to the last n minus k variable. Right. So those marginals or observables, right, we can get them if we knew the joint law of everything, we would know all of them. Interestingly, they can also be obtained from the empirical measure. And so fn1 of t and x, for example, is just the expected value of the empirical measure. The exact equality, however, stops being true if you go to the later one, but you have an almost equality. So I can write something like this. Sorry. X1, xk, right? This is the expected value of the tensorization of the empirical measure plus a correction that unfortunately is could be large if you take case large, so it's a correction of order k squared over n. And so this is the expected value of un of x1, right? Un of xk plus a big O of k squared over n. And here you see the relation between this the trajectorial approach, right, and what I'm calling the statistical approach. And you see why I'm saying that there's a loss of information, right? It's because if you know the empirical measure, then you will know the joint laws, right? The marginals, right? The reduced laws, but not the other way around, right? If I know the expectation of an object, I don't know the object. Right. Now, for a fixed k, f and k is a very reasonable function. Defined in a fixed and finite dimensional space, right? So this is the obvious interest of those marginals with respect to the joint law, right? The joint law was in this crazily large space, and that meant that I couldn't have any easy comparisons. But now if I fix k, none of that applies, right? I'm fine. So we could compare f and k, and the tensorized law, right, f tensorized k times, using any norm, any standard norm will work, right? Right. So for example, now I can use LP norms. If you prefer to use weak norms, you can use weak norms, right? So I can use Wasserstein distances. Right, very, very simple. That is great. So this leads me to another formulation of propagation of chaos, right? In the following way, right, if I want to have limits for any fixed k, right, f and k converges in some topology to a tensorized version. Now, moreover, there's an interest in this, right? You remember that when you when you want to check independence, right, you only need to look at pairs. And so actually, if we wanted to check propagation of chaos in that sense, we only need to look at Fn2. So equivalently, if Fn2 converges, for example, in the Wasserstein distance, we need actually a weak topology here to make this correctly. When Fnk converges, right, as n tends to infinity. As n tends to infinity. All right. That seems very, very nice. Much nicer than the joint law. Yeah, and that's one way of saying that the xi are almost IID again, right? For any fixed n, they cannot be perfectly IID, but almost IID, right? And all right. So we have this. And it seems this is nicer than even the empirical measure, you know, like ideal case. In fact, this formulation was introduced by CAC originally, and then Sneetman. And they are very popular formulation. But there is one issue and one drawback. And the big drawback is we don't have a good equation on Booth marginal. Now, we can get an equation on Fnk just by integrating the equation on Fn, right? Remember that I can get the Fnk in terms of Fn? I had an equation on Fn. Let me integrate that and see what I have. So let me call that a relation on Fnk by integrating the equation on Fn. And you have the following expression. Okay, so the beginning is very simple, right? And it's what happens when I'm integrating the equation on Fn, right? I have the self-interaction term because that depends on xi, so I get the integral, right? Or in the expression with the sum, right? None of the xj, j is larger than k, right? Because then again, when I integrate with respect to xk plus 1 xn, this goes straight on Fn and I get Fnk. But there is an extra term when those j's are above k. And then by symmetry, they are all the same ones. So I actually have this. Oh, and I forgot the divergence xi. And now I cannot find f and k, because now I will have, for example, this guy, xi minus xk plus 1. Now I can integrate with respect to xk plus 2 to xn, no problem, they don't show up, right? But I cannot integrate like that with respect to the last one. And the diffusion, however, is not a problem. And you see what happened, right? Now the equation is not closed, right? If I want to solve for f and k, I need to know f and k plus 1. And so I have a hierarchy of equation, right? Because I might want to start with fn1 or fn2, but then I need fn3, I need fn4, I need fn5, and so on, right? Now, this particular hierarchy is called the Bbjky hierarchy. And this is what makes our life extremely painful. Right, so that is the big drawback, because now I would very much like to have, you know, some sort of comparison between f and k and f tensorized k times, but I can't easily get one, because I would have to work with this equation on f and k, and then this would require a good control of f and k plus 1. And so I'm pushed back and back and back, right? And that is a huge technical difficulty. Okay, this is it for today, and just on time. So the plan for tomorrow is to start looking at some classical proof, right? And that will give us a bit of a better sense of what we can easily do with those formulations and what we cannot easily do. But I hope that you had a bit of an idea of at least how we could see, what are the various ways that we could use to see the system. From keeping the system of coupled ODE and SDE to using empirical measure, to using the joint law, to using now those notions of marginals. And I'll try to answer questions if there are any.
Yeah, thank you, Pierre-Emmanuel. The micro is open for questions if you want to ask audio questions.
Can we see Fn as a Markov chain? No. So Fn, the joint law, is now a deterministic object, right? So it's not random anymore. That's one of its attraction, right, in this third section. But now we are dealing with deterministic objects, so we don't need to worry about about anything else. It does satisfy a forward Kolmogorov equation, right? So here it is, right? So of course, you can say that it's the law of the Markov process, right? Which is true. It's the joint law of the xi. The xi do solve the Markov process, but it's not a Markov chain itself. And even the FNK, sorry, right? They are not, they are deterministic. And even this relation FNK involving FNK plus 1, it's not exactly something that is Markov, right? And it cannot be formulated like that, so it's something else. Any other question?
I have a question, please.
Yes.
Yeah, thank you for the interesting lecture first. And yeah, as we know, deterministic case is less used than stochastic one. And I found in the literature that people use, as you just showed us in the first part of this lecture, that we use the law of large number to expect the state, let's say xi, to be close to the solution of the Makin-Vlasov equation, right?
Yes, yes. But I'm actually going to give you proof of that tomorrow morning, tomorrow afternoon, sorry.
Okay, so my question is how to proceed to get a Millfield limit in the case we have a deterministic setting. I mean,
it's the same. Because there's noise everywhere, there's randomness in any case, right? Again, this is very, very important. Whether I have a Brownian or I don't have a Brownian, I have randomness, and that randomness comes from my initial data.
Yes.
Right. So even if you ignore the Brownian, the kind of strategy that I described here is the same, right?
Okay.
So the proof I'm going to show you tomorrow, right, will be valid whether sigma n is equal to 0 or sigma n is not equal to 0.
Okay, I see.
Right. There are differences between deterministic and stochastic.
Yeah.
And we'll start. Well, we'll mostly discuss them on Thursday when I'll go to more recent and then more difficult cases, right? But at the elementary level, they behave in a very similar way.
Okay. And just another question. Back to the system of xi bar.
Yes.
You said that, I mean,
yeah.
we can drop the index I.
Yes.
To get the Makin-Vlasov process.
Yes, because, right, you get to here first.
Yes.
And you get to here by noticing that all those conditional expectations, actually, they are identical. They are the same.
That's the same. Yeah, sure. And what about the initial position? We still have different start points.
Yes, but now you have n copies of the same process. Right, okay. Because the law initially it's the same for every one of them.
Okay.
Right. So the only difference here that you have from one index I to the other index I, right, is you've chosen a different realization of that law, and you've chosen a different realization of the Brownian.
Okay.
But they are all equivalent, right? It's just like, imagine I have n copy of a Brownian motion. And I'm going to tell you why would you want to solve n copy of the same, of what is actually the same object, right? Just solve one.
Yeah.
Right. And that's what is going on here.
Okay. Thank you so much.
Question, please.
Yes.
When have the law of xi bar, and when we define the empirical measure, does we have the limit goes to 0 when n goes to nth?
So sorry, I missed actually the first critical part of your sentence. Can you try speaking a little bit louder?
When we define f, the law of xi bar,
Yeah.
just right here,
Yes.
and we define the empirical measure, does we
Yes.
have convergence with the Weierstrass distance when n goes to empty, for example?
All right, so this is something that I'm going to talk at length tomorrow. There's a bit of a tricky answer here. Because the empirical measure is a random object. So what we could get, right, by compactness, we could say that there is a subsequence of the empirical measure that is going to converge to something, right? But that something would also be a random object.
Yes.
And what we want actually, right, let me go to, let's go to the W-1, for example. Here, I want that the empirical measure converges to F. F is a deterministic object. Right? So that is a lot harder for a random object to converge to something that is deterministic.
Yes.
But of course, the question here, right, is do we have so in general, do we have that the expectation of some Wasserstein distance, right, between mu n and f, do we have that this converges to 0 as n tends to infinity, right? That's what we would have to prove.
Yes. Yes.
Right. That's what I'm going to prove tomorrow.
Okay. Okay. Great.
In some cases.
Thanks.
But that's, yeah.
In some cases, and some assumptions, of course.
Yeah. Yeah.
Thank you. Thank you a lot. And a great course, by the way. Thank you very much.
Thank you. Thank you.
Thank you, Sarah and Abduli. Are there any other questions?
Otherwise, I'm going to ask the same question that I had asked yesterday. How's the tempo of the course? Is it going too fast? Is it going too slow? What do you think today?
Great for me. Great.
Yeah, it was good today as well. Thank you.
Okay, I think, yeah, somebody else agrees in the chat. Thanks.
I would like to recall everybody that there is a YouTube movie now, which is live during the talks of Professor Jardin. And you can go back to it to have to rewind if you miss some part of the talk. And you can also